In this video, we will now take a look at hypothesis testing on the mean where we use the p-value approach. So as opposed to the critical region approach, we also have the p-value approach. We'll talk about how to do hypothesis testing with the p-value approach. We'll look at how it is different from the critical region approach, and we'll also discuss the pluses and minuses of each approach. First, the p-value approach is still a 6-step process, which is summarized here. Let's quickly read through these. We'll put this in practice in a little bit. Step 1 is to define your pair of hypotheses. Step 2 is to note the level of significance alpha. Step 3 is to determine the type and tail direction of the test. And these are exactly the same 3 as it was in the critical region approach. Then step 4 is a little different. You're going to compute your test statistic using the sample data. In the critical region approach, we didn't compute our test statistic until step 5. With the p-value approach, step 5 is to find the p-value, then make a conclusion about the null hypothesis. Making a conclusion about the null hypothesis was part of step 5 in the critical region approach. And then step 6 is the same between the two. Make conclusion about claim and interpret your results. So if we're going to do the p-value approach, the first thing that's needed is an understanding of what a p-value is. Let's take a look at that. Here is the definition of a p-value. A p-value is the probability that the test statistic will take the computed sample value or more extreme value. In other words, the p-value is the area from the test statistic through the tail. So let's go through that, explain it a little bit more using this picture here. This could be either a t-distribution or a standard normal distribution. Let's suppose you're doing a right-tailed t or z test. You'd compute the test statistic, and let's say that's right here. Then the meaning of the p-value is the area from here out through the tail. This right here, that area would be the p-value. Let's say you're doing a left-tailed test. With a left-tailed test, you compute the test statistic. Let's say it comes up somewhere right around here. The p-value then would be the area from that test statistic over into the tail. So the smaller the p-value, meaning the smaller the area, the more extreme the test statistic is. So the question is, how small is small enough for the test statistic to be too extreme? That's precisely where the decision comes into play. If a p-value is less than or equal to alpha, the level of significance, then it's too extreme, the test statistic that is, and we want to reject the null hypothesis. If the p-value is greater than the level of significance alpha, then we fail to reject the null hypothesis. Since the p-values are areas, you should be able to compute p-values from the standard normal distribution table when performing a z-test. So when you have a z-test, you should be able to do this p-value approach. But when it comes to a t-test, you would need software to compute the p-values because our t-table has critical values in it, not areas. So we would need software to give us the p-value. So if we do any t-tests with the p-value approach, I would show you how to use software to come up with that p-value. Now that we've got a p-value defined and where you should be able to use it, let's now compare the p-value approach directly to the critical region approach. With the critical region approach, we first drew our graph, we shaded in the rejection region. Let's say it's a right-tail test, which is this example here. We shaded in the rejection region and found this ever so important critical value right here. Then we did a computation of our test statistic, and we had to see if the test statistic fell in the shaded region. If it did, then that test statistic was considered too extreme, so we would reject the null hypothesis. If it fell over here, the test statistic that is, in the fail to reject region, then we would fail to reject the null hypothesis. The p-value approach is somewhat the other way around. Over here, the size of this tail was determined by whatever alpha is. Whereas over here, we first compute the test statistic, and then the test statistic will determine the size of the p-value. The area from the test statistic out through the tail is what we call our p-value. Then that area gets compared to the area of the yellow area, which is the level of significance alpha. So this whole thing here is alpha. And if your p-value, which is this shaded green area, if it's smaller than this whole area, which would be the level alpha, then this test statistic is considered too extreme and we would reject the null hypothesis. Now that we have a little bit of a conceptual understanding of the difference between the methods, let's now look again at the 6-step approach and really highlight what's different in the 6 steps from the p-value approach as opposed to the critical region approach. As you can see here, I've already highlighted step 4 and step 5 in red. Those are the 2 steps in the p-value approach that are different from the critical region approach. Steps 1, 2, and 3 and step 6 are exactly the same between the 2 approaches. So with the critical region approach, you computed the test statistic in step 5, whereas with the p-value approach, you compute their test statistic in step 4. And then from there, we find the p-value in step 5 and make a conclusion about the null hypothesis. Now that we also see a difference in the 6-step process, why do we even have multiple methods? There are multiple ways to answer this question, but for me personally, the power of the critical region approach is that you can really see exactly what's going on. So you've got your curve, whether it be a standard normal curve or a t-distribution. Then you shade in the rejection region based on the direction of your test and whatever alpha is. Alpha is the area of this space right here. And then you can visualize when you go to compute the test statistic, does it fall over here? That would be our acceptance region, or does it fall over here in the rejection region? The visualization is powerful when it comes to doing the critical region approach. Now, potential weakness of this is that you'd have to completely redo this if you changed alpha. That would change the scenario for us. Whereas with the p-value method, the p-value method provides the smallest level of significance at which you would need to reject the null hypothesis. So you can actually see how low you can go in alpha before which you would have to end up rejecting the null hypothesis. So that's a plus of the p-value approach. Also, computers very quickly, easily give you p-values. So that's another advantage. The disadvantage, in my personal opinion, is it's just a bit harder to visualize exactly how the p-value method works. If you understood the previous couple of screens well, then perhaps that is not true, but it's a little bit more challenging to visualize than the critical region approach is. So they both have their strengths and weaknesses, but when it comes to doing z-test, we should be able to use the critical region approach or the p-value approach. With a t-test, we would need a computer software to give us the actual p-value. Whereas with the critical region approach, we can do that without needing computer software, with specifically a t-test. So now that we've established the difference between the two and how the p-value method works, let's look at a problem that we solved in a previous video where we did hypothesis testing on the mean, but we did it with the critical region approach. Now we will do it with the p-value approach. Hopefully this problem is familiar to you. Unfortunately, arsenic occurs naturally in some groundwater. A mean arsenic level of 8 parts per billion is considered safe for agricultural use. A well in Texas is used to water cotton crops. It's tested on a regular basis for arsenic. A random sample of 37 tests gave a mean of 7.2 parts per billion of arsenic, and based on previous studies, assume the population standard deviation of arsenic level is 1.9 parts per billion. At a 1% level of significance, should we believe the claim that the mean level of arsenic in this well is less than 8 parts per billion? So again, we've already done this one with the critical region approach. Let's now do it with the p-value approach, and of course, we should get the same results in the end. So step 1, we need to define our pair of hypotheses, and let's redo that in case you don't remember precisely from the first time around. The claim in this case is that should we believe that the mean level of arsenic in this well is less than 8 parts per billion? So the claim is mu is less than 8. The complement of mu is less than 8 is mu is greater than or equal to 8. And of course, the null hypothesis is the one with the equality. So the mu is greater than or equal to 8 is the null hypothesis, and the other one is the alternative hypothesis. Step 2, we want to note our level of significance. They give us a 1% level of significance in the problem, so alpha is 0.01. Step 3, we need the type of test and the tail. The tail direction is determined by the alternative hypothesis. We've got mu is less than, so that means it's a left-tailed test. So we have a left-tailed, and in this case, we have The population standard deviation is 1.9 parts per billion. So that's sigma. So sigma is known. And we also have a sample size that's greater than or equal to 30. So we're doing a z-test. So this is a left-tailed z-test. So that's all the same as it was in the previous time we did this. Now step 4 changes. We are going to compute the test statistic right now. So we're computing the z standardized test statistic. Again, that is x bar minus mu. X bar, we had a mean from the sample of 7.2, so x bar is 7.2, minus the hypothesized mean is 8, over the standard deviation of the population is 1.9, by the square root of the sample size, and the sample size is 37. And of course, if you're putting this in your calculator, make sure you have the top in parentheses and the bottom in parentheses, and this gives you approximately negative 2.56. In step 5, we need to compute the p-value and then make a decision about whether we should accept or reject the null hypothesis. So technically, you do not need to draw a graph for this particular part, but I'm going to do it just since this is our first problem. We've got, again, a standard normal distribution. We're doing a z-test. And we got a test statistic that's negative 2.56. And the tail of the test is left-tailed. So that means this out here, this area, is precisely what we need to find. That is our p-value. And then, to make a determination about the null hypothesis, we're going to compare the p-value to the 1% significance level. So first, we need to get that p-value. So we need the area under the standard normal curve to the left of negative 2.56. Hopefully at this point you are comfortable reading your standard normal distribution table. The area to the left of the z-score negative 2.56 is precisely 0.0052. So this is equal to 0.0052. So we have a p-value of 0.0052. Now in step 5, not only do we compute the p-value, but we also need to make a decision about the null hypothesis. And the decision is based on comparing this thing, the p-value, to the significance level. If the p-value is less than or equal to the significance level, this test statistic is considered too extreme and we want to reject the null hypothesis. Otherwise, you would accept the null hypothesis. Well, this number is in fact less than or equal to 0.01. So this test statistic, which yielded this p-value, is too extreme. So because of this, we want to reject the null hypothesis. So we're going to reject H naught. Now in step 6, we go back to exactly what we were doing with the critical region approach. We need to interpret our results here and make a decision about the claim. So we're rejecting H naught. Rejecting H naught implies that we reject that mu is greater than or equal to 8, which then means we would accept that mu is less than 8. We would accept the alternative hypothesis, which is in fact the claim. So we are going to accept this claim, and we're accepting it at the 1% level of significance. So let's write that out. At 1% level of significance, we accept the claim that the mean amount of arsenic, that the mean level of arsenic is less than 8 parts per billion, which is exactly the same result we got when we did this computation using the critical region approach.